Hi, and welcome to another video on the Zero to ASIC course channel. And this time I'm going to be talking with Uri Shaked about how he built SiliWiz. So I'll just add Uri to the stream. How's it going, Uri?
Hi, Matt. All is good.
All is good. Yes, probably if you've been paying attention, you can't have missed SiliWiz, which I've got up on the browser here. And this video is not going to be about how to use SiliWiz or really a demonstration. I've already got some other videos. I'll just mention the main features. We've got these different layers that we can draw on here. So you can select one and draw it. You've got this preset window, so you can clear and load different things. Cross-section and DRC, so you can see how the three-dimensionality works. And then finally the simulation that is all adjustable in real time. And as you change these things, let's go to, say, NMOSFET. As you change these things, the simulation updates in real time, which is a really great way of learning interactive silicon wizardry. That's why it's called SiliWiz. And if you want to learn more, then click on the lessons. But today we're going to be clicking on the GitHub repository. It's an open source project. And we've got Uri on the line who built SiliWiz, basically. I drew some stuff on paper, and then Uri did the magic. So, Uri, we've got some questions for you. The first one was, tell us about the kind of the flow, because there's quite a lot of stuff going on. Like, it's not all running in the browser. There's like, it communicates to another server, this kind of stuff.
Right. So let's start with a high-level overview of the architecture of the application. First of all, as you mentioned, it's open source, and you have this little AutoCAD here that you can click to get the source code repo. And the source code is available on GitHub. And as you said, like, most of the magic happens in the browser, but actually the magic part doesn't happen in the browser. So let's dive into that. There are three major parts of the application. The first part is the front end, which is what you are seeing and interacting with. And then there is also like the extraction engine and the DRC engine. So that takes your drawing, whatever you draw on the canvas, and converts it into a file that could be simulated. That's the extraction process. And there is also a DRC engine that checks if you have any errors or violations of design rules. So these are like the second. This is the second part, the extraction and the DRC engine. And the final part is the Spice. It's the simulation engine. So whenever you make any changes here or to these parameters, you can see this graph, which is a result of SPICE simulation that is running automatically whenever you make changes. So the three main parts are the front end, the DRC, and the circuit extraction done by Magic, and the simulation done by NGSpice.
Yeah, and there's just when you say done by Magic, we have to differentiate here. So Magic is an old school 40-year-old VLSI tool currently maintained by Tim Edwards at eFabulous, and it's still like a crucial part of the open source ASIC flows for circuit extraction and DRC and these kinds of things.
And that's exactly what Magic brings to SiliWiz, these two functions of DRC and the circuit extraction. And interestingly, Magic is the only part of the whole thing that is not running in the browser. We are running it in the cloud. So whenever you make any changes to this circuit, this actually goes to the cloud, performs the circuit extraction, and sends the result back to the browser. And if you click this checkbox here, you can actually see the result of the circuit extraction. Like this is what Magic returns. And once we get this result, we create a SPICE file, which is then simulated in the browser.
Awesome. Magic.
And that's the flow.
And that's the flow.
Magic flow of
Magic
SiliWiz.
Right. So maybe you can. So when we were getting ready to launch it, I didn't really know how many simultaneous users we were going to get. I thought probably it would top out at like 500 or 1,000. And I said, do we need to worry about scalability? Do we need to like test it? And you said no. So how is it that, like, how many instances of Magic do you run on a server, and how do you know when to start up a new instance, and how does all that stuff get handled?
So this is actually more magical than the magic part, and we'll get to it in a moment. Before that, other than Magic, everything runs in the browser. So for the simulation, the Spice simulation or the front end to be scalable, it's very easy. We are hosting it on right, and we are hosting it on Cloudflare pages, so they handle scaling. We don't have to worry about that.
Right.
We can get as many visitors as we want, and it will scale. So the only part of the system which we actually need to worry about the scale of is Magic. And if you are wondering about how this works, how do we do this little glue between Magic and the browser? There is a very small server that we are running, written in the Go programming language, and you can see it's around, let me make the font a little bit bigger. It's around 100 lines of code, and it basically runs an HTTP server and gets requests, write them into a Magic file, runs Magic. You can actually see the list of commands that we are sending to Magic. The first one does the DRC, and then the other ones take care of the circuit extraction. And finally, it has two outputs, the Spice file and a list of DRC items, and it sends them back to the browser. So we have this Go program, which is compiled into an executable. And instead of having to worry about setting up servers and scaling, we are actually taking this Go program and wrapping it in a container, and then using the Google Cloud Run service to just run instances of it as we need. So here is the Google Cloud Run console, and you can actually see, if we look at the instance count, for instance, that yeah, it's a day full of puns. That we had a very big spike here, where we had at the top of it we had like 28 servers or instances of the servers running concurrently. 12 of them were active, 16 were idle, just ready to handle any possible if the search gets bigger. But normally we keep between 1 and 2 active instances. So basically, the only thing that stops it from scaling is the amount of compute that Google can allocate to that, and the money in our pocket, because eventually we need to pay Google for the scaling. And that's why I said you don't really need to worry about scaling. This is all handled by Google, just using Google Cloud Run.
And how much are we paying a week, Uri?
That's a good question. It's a bit hard to tell right now, because we need to dig in a lot of reports. But based on my experience with Google Cloud Run and the number of requests I'm seeing here, I would say everything you see here is not more than $20 or something like that.
Right.
It's definitely affordable.
Yeah. But if you do want to help and support, then make sure you check out the Tiny Tape Out website or the 0 to ASIC course website and support us that way.
Yeah, I mean, if we are talking about costs, then the costs for running the service are nothing compared to the time and effort we're putting into. Yeah, I mean, that's the big cost. Man hours.
Person hours.
Person hours.
Uri hours.
1 person hours.
Yes.
Yeah.
Okay, great. So, and how do you tell So you're just basically giving this container to the Google Cloud service. I'm totally ignorant about this stuff, really. I like the servers that I interact with is like DigitalOcean droplets. So you spin up a whole Linux machine, then you like install the stuff on it. But this sounds like it's more, you make a Docker container and then you just give that to Google Cloud and then it does the hosting of it like transparently on as many servers as is needed.
Yeah, right. There are a few services that can do that. What I like about Google is that it's, first of all, Google, so they have a reliable and scalable infrastructure, and it's pretty easy to set up. Like once you have a cloud account, you set up a couple of configuration files, basically point them at your container image, and it works. As long as you have an app that is just an HTTP server running on some port, it just works.
Okay. So was it difficult to get Magic to run inside that?
Actually not. My first attempt was to compile Magic to WebAssembly, just trying to cut the cloud entirely. And I guess with some work, it could eventually be compiled into WebAssembly, but one of the challenges was that I think the original code was written way back, and compiling it with modern compilers produces some errors about types and that kind of stuff, like functions, prototypes that aren't properly declared. And if you wanted to compile it to WebAssembly, you need to go to the source code and fix those those warnings or errors. And it just made sense to not spend that effort right now and put it into the cloud for $20 a month or whatever it costs.
This is the MVP, see whether it's like a useful tool, whether how much use it gets and so forth. So yeah, we don't want to push the boat out too far right at the beginning.
There is also another disadvantage to WebAssembly, which is sometimes you get pretty large binaries. So the user has to wait until those download and run inside the browser. Whereas if you run it on the cloud, the user just has to send a tiny magic file and get a result. So it's like another trade-off that sometimes makes it easier to just run stuff in the cloud and not spend effort and time compiling it into WebAssembly.
Okay, right. Okay, so why don't we talk a little bit more about the front end then? So what is the framework that you're using? Is it like a JavaScript framework? Is it like Material UI? Is it what? There's like loads of these kind of frameworks to build up applications easily. Are you using something like that?
Yeah, so I'm using a pretty new framework called SolidJS. It's very new in terms of frameworks. It's a bit similar to React. For those who are coming from the front end, they will probably recognize this. It looks very similar to React. It has some new and interesting concepts about reactivity. And this was my first project using that framework. So usually when working on a new project, I like to try out new stuff that seems promising. And in this case, it was a pretty good experience overall. One of the disadvantages of Solid is that it's brand new, so there is not a lot of documentation, and I had to spend some time fighting issues and reporting them in GitHub. So it's a trade-off. But I think one of the advantages here is that the syntax is very similar to what React uses. So if at some point we decide that Solid isn't a good choice and we need to convert this to React or some other similar framework, there will be some work, but at least the basic syntax is similar.
Right. Okay. So you draw your stuff on the canvas, and then that actually gets made into a magic file, the .mag files, right? Because those are just simple text files. They're just like a list of polygons and what the layers are. In fact, you can, if you with the Show Spice button clicked, you can actually download the magic file, can't you?
Yeah, let's do that. I'll download the magic file, and then I think I can just drag it into the browser and see it. Yeah. So it's basically a list of rectangles and the layers. So it's very similar. Like if we open one of the presets that so this is the list of presets that is coming from the GitHub repo. Which one were we looking at? The inverter, right? Mm-hmm. So if we open the inverter, we can see like there are rects here with layers, and there are rects here with layers. It's super similar. Like there is 2 anvil here, and you can see that like there are 2 anvil here, and even like x96, like it's the same information, just a slightly different format.
Yeah. And then that's sent over to the Magic server, when then we get returned with the DRC and the spice. Then the final bit is the DRC is just shown when you're on the cross-section tab. If there is a DRC error, it just like highlights where the problem is.
Yeah, we can actually see this in action, I think, if we open the browser network tab. And make some change. Let me try to make something that would probably cause a DRC issue. Yeah, so you can see there is a DRC issue here with the annual spacing. And if we look at the network tab, we can see there is like this request that we send with the magic file. This is the magic file that was generated for the circuit. And then the result is it has the spice file. So this has the extractor circuit that we can see here below. And then also all the output from our running magic. And we can see, let me see if I can even zoom in a bit. Don't know if I will be able to, but I will try. Yeah. It's a bit hard to see, but you can see there is this SiliWiz DRC item with some information about the DRC error, right? You can see it like
actually, we don't. I think that window is not being shared, so we don't see that. We're just seeing the magic output.
Oh, yeah. So let's just hold on. Yeah, let's just do something really dirty and use this text box to show the magic output. Yeah, so this is the magic output. It's actually I have a better idea. Just console log this so it will be presented as text.
Okay.
So so now you can see like this is the output we are getting from Magic, and you can see like which version of Magic, even when I compiled it. And one of the lines here says SiliWiz DRC item, and it has information about the error, the same information that you see here. And you may ask yourself, how comes that Magic knows about SiliWiz? Like, why is the name SiliWiz included in the output from Magic? And the reason for that is that we tell Magic to print this line. If you check out the commands that we pass to Magic, there is a command that just goes over the list of DRC items.
Okay.
And it prints each of them in a different line, and it adds this marker. So when SiliWiz sees a line that starts with SiliWiz DRC item, it knows to take it, to parse it out of the Magic output. So that's how we do the connection between Magic DRC and the front end.
Great. And then the final part of the puzzle is the spice.
Right, the spice, this simulation that you are seeing here.
Spice is life.
Spice is life.
So so we're using NGSpice. And we could be using other simulators. Do you want to say a word about the other simulator?
Yeah, there is an interesting simulator that Wilton has been working on. So if you check the Sina branch, let's just go. Yeah, if you check the branches here, there is another branch called Zina, and you can find his work and play around with it. I don't think he has played with it lately, but the thing is, since the simulator, and if you look at the source code, the simulator is actually just a function that we call and does all the smart thing that's here. So if we go into sim, there is a file called simulate, and this function gets a SPICE files and a list of signals, and it updates the simulation results. So it's pretty easy to swap NGSpice with something else. Mm-hmm. And maybe it's a good time to answer how we use NGSpice. So we compile NGSpice to WebAssembly, and whenever you run the simulation, or let me clear this window so we can see it from scratch.
Let me just first mention that we had some help from Holger, who's the maintainer of NGSpice. So thanks, Holger, to help minimize NGSpice. So he added some, I think they're just like defines that you could undefine, so we could turn off a bunch of things that we don't want, because really we're only interested in resistors, capacitors, NMOS and PMOS. So by making some simplifications, we're able to get how small did you get it in the end? Was it like 2 meg or something?
Yeah, how low can you go? So that's what we asked him, and he actually made a spatial branch for us, minimal NGSpice. You can see, I guess the last commit here is about removing a bunch of stuff.
Yeah.
Yeah, make a minimal version.
On my Linux version here, it's 6.7 meg.
Yeah, so the WebAssembly version was 5.5 megs, and then when we, after removing all the stuff in this commit, we got it down to 1.8 meg. Right. And that's even before compression, but when the browser downloads it, it's compressed, so it's... I think it's not even zipped. I think they use Bradley or some other more modern compression. So it's. And
then is that cached? Like if you go back to SiliWiz like 2 days later, is it still in your browser cache?
Yeah, we can look at it now. I just refreshed the page, and we can see that all the stuff is coming from, or most of the stuff is coming from this cache. Even if we look for the SPICE, we can see. 44 bytes, 444 bytes. It's just like ask the server, was it modified? And the server said no. And if we disable cache, we can see it's about 0.5 megs.
Right.
Yeah, with the compression. So not significant.
Amazing. Yeah.
It's just like downloading another JPEG file or something like that. Yeah, exactly.
A picture. Yeah. So what is WebAssembly?
So, wow, that's a big question. So WebAssembly
give us the executive level summary.
So WebAssembly
as the executive of SiliWiz, Uri, please tell me, what does WebAssembly mean?
WebAssembly is a way you can run programs compiled in different languages on the web. So it's a very low-level virtual machine, and there are compilers that can take code in C, in Rust, in Zig, even in some variant of JavaScript that is called AssemblyScript, and many other languages, and compile them down to that virtual machine. And one of the advantages is that you can take existing programs like Spice or Magic that were written in C or C++ and use the WebAssembly tooling to compile them into a binary that you can run in a web application. But that doesn't come without challenges. One of the challenges...
Just to interrupt, so where does that web application run then? It runs on your local browser, right?
Right, just like JavaScript runs in the browser, there is also like the WebAssembly virtual machine. And the JavaScript code can load a WebAssembly binary and interact with the virtual machine while the binary is running.
Okay, so it's a bit like being able to translate a C program into JavaScript so that it's compatible with the browser environment.
I I think it started that way, but nowadays WebAssembly is its own thing, and you can even run WebAssembly on embedded devices.
Okay.
So there are WebAssembly engines that run outside of the browser, written in Rust, for instance, like WasmTime. They are unrelated to the browser. And there is even, I think, experimental support in Docker for running WebAssembly binaries. So if you compile Spice to WebAssembly, once you can run it inside Docker, for instance, regardless of the operating system that you are doing. So it's becoming, it's only the beginning, but it might become a new virtualization technology, or a way to make applications more portable. And with WebAssembly come many challenges. One of them is that programs like Spice, they work with files, but you don't really have files in the browser.
Yeah. And
So
loads
some
of
the
Linux and Unix programs are expecting like streams, IO streams and pipes and all this kind of stuff.
Right. So some of the tooling around WebAssembly actually simulates a file system, and you can see in the code where we use we actually called NGSpice that we are using methods that that are writing files to a virtual file system with the circuit, and then reading the result from a virtual file. So
because that's like how Spice is normally run, isn't it? You give it input files and then it creates an output file.
Right. So we are running Spice in the browser, and we are doing a bunch of optimizations to make sure that we are loading Spice once and then sort of making it reread and rewrite the files whenever we need to run your simulation. But if we wrote the simulator in JavaScript, it would just be a function that gets the circuit and returns the result. But since we are using NGSpice, we have to sort of work around the fact it's a Linux program and use this abstraction of files to communicate with it.
Right, makes sense. Okay, great. Okay, so I think the place where I want to end is if you can just go back to the Git repo.
Maybe just before ending, I need to give a shout out to, I think it's also mentioned here, to EESIM, which was the first by this guy, Daniel Chutnis, which was the first project that I have seen which compiled Spice to WebAssembly. So EESIM is also a really cool project. Go check it out. And we built upon Daniel's work to run WebAssembly Spice in the browser.
Cool. Thanks, Daniel. Yeah, so if you go to the top level of the SiliWiz repo, yeah, so it's an open source project. If you want to contribute, then open a pull request or an issue. We're kind of in MVP mode at the moment, so we're going to like collect ideas and information and issues, but we're kind of going to just not going to be rapidly working on it, just to set expectations there.
When did we get 61 stars?
I don't know.
Didn't just
recently
noticed it happened.
Yeah.
Okay.
And the thing that I was like super impressed was when I was giving feedback about like getting the layers the right height and the right color and so on, I was able to play around with it without having to like install it locally, because you have this kind of GitPod thing set up. So if you scroll down a bit so we get to the README, you've got these little badges here.
There's this GitPod ready to code.
Ready to code, yeah. So explain to us a little bit about GitPod.
So I think GitPod is very much, if you are familiar with Wokwi, is like Wokwi, but for code repos. It lets you open a repo in a click and just play around. So, for instance, once you click this button, you have to wait a few seconds until they launch
it takes a couple of minutes, I'd say, when I tried it. Yeah.
But once it's loaded, I tried to prepare it in advance, but it timed out. Once it's loaded, you can see a code editor that is running in the cloud, and it's also compiling and letting you see the source code as you make changes. So I don't know why we have 2 copies here, but here you have a copy of SiliWiz that is running inside GitPod.
Yeah.
And this means you can just go to any of the source files, like let's put them
The layers
side
what
by
we were
side.
just talking about, yeah.
Yeah, the layers, and let's say we want to change the layer, the color of the substrate to salmon. So we just type here salmon.
Yeah.
And we didn't even have to save. It just rebuilt the app.
Amazing.
And now you can see the changes.
Yeah.
Super rapid prototyping.
Yeah. Especially, and for me, it was made it so much easier to contribute because as someone who's really unfamiliar with like modern web development, I didn't need to, I don't know what I would have needed to have done, like install Node.js, or like last time I had to played with something out around and I needed to install Node, I got stuck on installing Node. So it was really nice to contribute to this project because I could just run it with GitPod. So I think you've done some really great work here, Uri, in not just in the building such a cool application, but also the way that it's structured and architected so that it scales and so that it's easy to fork and make pull requests to and experiment with in the browser. So really excellent job.
Thanks, Matt. And that's a good point, actually. You can not only change the code with GitPod, you can actually use their tooling to make pull requests back to the repo. So you don't even need to check out the code to your computer to make changes, test them, and make a pull request.
Amazing. So is there any last thing you want to add, or we're going to draw this to a close?
Yeah, I think we gave the audience a good overview of how SiliWiz work, and let's leave it as an open question to the people who watch this video. Do you have any other questions or things you would like to learn about SiliWiz or how we build it? Just let us know.
Yeah, and I'll leave a link to the, we've got the Tiny Tape Out Discord community server, which is open to join. And in there, we've got a SiliWiz channel. So that's where we're discussing SiliWiz. And there's already some interesting discussions going on there. So feel free to join, make some, find some bugs, make some pull requests. Let us know how you get on. And thanks for watching. Bye.
Goodbye.